Welcome to the Conquest of Cold, a story about how scientists and engineers steadily push temperature down toward absolute zero. Over the next slides, we'll trace that relay race from simple thermoscopes to industrial cryogenics, highlighting the ideas and inventions that turned cold from a sensation into a practical engineering tool. In a modern liquefied natural gas plant, temperatures like 150 Kelvin or 112 Kelvin are engineered with astonishing precision, but those numbers are the result of centuries of progress. This presentation tells how we learn to measure and control cold, turning a vague feeling into a reproducible industrial language. For millennia, cold was only a subjective sensation, but building a science required a tool and a shared vocabulary. Inventors first set out to quantify the invisible, creating instruments and standards so that different observers could agree on what a temperature actually is. The path to a universal temperature language was gradual. Early thermoscopes showed change. Fahrenheit introduced reproducible reference points to stabilize measurements, and Celsius proposed the simple centigrade scale using the freezing and boiling of water, giving scientists common benchmarks for comparison. Once measurement existed, debate shifted to the nature of heat itself, and for a long time, the elegant caloric theory held sway, imagining heat as a conserved fluid flowing from hot bodies to cold ones, a picture that explained some observations but contained a fatal inconsistency. Careful experiments eventually showed heat is not a fluid but a form of energy. Rumford's observations of friction and Joule's quantification of mechanical work proved that heating could be generated by work, leading to the idea that energy is conserved and heat can be accounted for quantitatively. Knowing heat is energy begged a deeper question: what rules govern its transfer and limits? Scientists needed laws to describe efficiency, irreversibility, and the theoretical boundaries of cooling. So they developed a framework to map how engines, sinks, and temperature differences interact. From those laws came a roadmap toward absolute zero. Carnot showed efficiency depends only on temperature differences. Clausius formalized the second law and introduced entropy, and Kelvin synthesized these ideas into an absolute temperature scale independent of any particular substance. Kelvin's scale revealed a theoretical finish line called absolute zero, the point where classical motion would vanish and temperature reaches its minimum possible value, defining a clear experimental target and kicking off the long race to approach that limit in the lab. With the theoretical map in hand, attention turned to the stubborn challenge of liquefying the so-called permanent gases that resisted all previous methods. Engineers and experimentalists pushed heat exchange, compression, and expansion techniques to their limits in pursuit of ever lower temperatures. Early breakthroughs shattered the idea that gases were immutable. Faraday showed gases like chlorine could be liquefied, and later engineers such as Cailletet and Pictet produced flashes of liquid oxygen by clever compression and rapid expansion, proving liquefaction was a feasible, if difficult, goal. A major practical advance came from James Dewar, who tamed liquid hydrogen by inventing cascade refrigeration, using colder liquefied gases to pre-cool others, and by creating the vacuum flask, the foundational storage technology that minimized heat transfer and made handling ultra-cold liquids possible. Heike Kamerlingh Onnes took the next leap by liquefying helium at about 4.2 Kelvin, a methodological triumph that also yielded an unexpected discovery: superconductivity, a quantum phenomenon visible only in the profound cold near absolute zero, and opening whole new fields of physics. Winning the race to the bottom was only part of the story. The next challenge was industrializing cryogenics, making processes practical, efficient, and economical so that cooling could move out of specialist labs and become a large-scale utility for industry and medicine. Two engineers, Lindy and Claude, provided the playbook for industrial cryogenics. Lindy refined vapor compression and countercurrent heat exchange to enable efficient cooling, while Claude's work recovery expansion engines boosted performance, together creating scalable methods for large-scale air separation and liquefaction. Modern LNG and cryogenic plants are direct descendants of those pioneers, evolving into optimized cascade processes, mixed refrigerant cycles, and turbo expanders that apply century-old principles in refined, highly engineered forms to achieve the temperatures we rely on today. You can visualize the whole journey as a thermal ladder. Each drop in temperature corresponds to a discovery or method developed by the pioneers, from pre-cooling principles through liquefaction stages to final subcooling techniques, all balanced against the underlying laws of energy conservation. Today, the glowing numbers on a control room monitor are more than data. They're the living language of a scientific heritage, and the work of Kelvin, Carnot, Lindy, and Honest continues as an operating system for modern cryogenics, a continuous conversation between physics and engineering. The conquest of cold sparked a revolution in both technology and theory. Artificial refrigeration reshaped food supply, medicine, and space exploration, while the quest for absolute zero removed classical noise and revealed quantum mechanics, catalyzing entirely new fields and applications. This relay race of discovery was fundamentally human, powered by theoretical insight, experimental grit, and practical engineering, and it stands as a testament to building new knowledge on the foundations laid by those who came before, passing the baton from era to era. The race isn't over. Researchers now pursue microkelvin and nanokelvin temperatures to enable quantum computing, discover novel superconductors, and explore exotic states of matter, suggesting that the deepest secrets of the universe may still be hiding in the quiet of extreme cold. Thank you for joining this tour of how we learn to measure, understand, and harness cold. The story continues in labs and plants around the world, and I hope this overview inspires you to look deeper into the techniques and ideas that make modern cryogenics possible.